All right, folks, we'll get started. My name is Sandeep. I'm the field CTO at Hasura, and today I'm going to be your host. And I'll take you over an overview and a deep dive into what we call the supergraph architecture. This is going to be a classical three-act webinar. We'll start by kind of defining the problem. We'll take a look at the architecture, and I'll give you a brief overview of our own implementation of this architecture with some infrastructure magic dust kind of sprinkled on top of the architecture itself. So that's what we're going to do in today's webinar. If you have any questions, please keep them coming in the chat. Would love to kind of answer any questions. If you have any feedback, would love to incorporate that as well. Please do not shy away from posting any questions in the chat. So with that, I'll get started. And the first act, or rather the pre-act message, is a quick introduction to Hasura for those of you who are new to Hasura. If you haven't had a chance to check out the website or more information about us, I can give you a quick snapshot of it. We are about 180 people distributed worldwide, headquartered in San Francisco, well-funded from venture capital firms, and have been kind of building developer tooling for the last few years. And we've seen some good adoption in the developer community, both from startups, indie developers, and from Fortune 100 and Global 2000 companies, and have a fairly successful open source product that's been downloaded several hundred millions of times, and is very active community on Discord and on GitHub. So if you do check us out, please do come participate in the community, join the community. You'll find a warm bunch of folks there ready to answer any questions that you may have, and ready to welcome you into the fold of champions who answer questions for other folks as well. With that, a lot of what we talk about today is based on our learnings from the impact that we've been able to have in several developer organizations. Now, these are Fortune 100 companies, the world's largest social media company, the world's largest healthcare company, the world's largest bank, I guess, all of your Fortune 100 companies with lots of developer teams, all of them trying to build the best API that they can possibly build to help support the products that are getting built there now. So a lot of our learnings, a lot of the stuff that you're going to see in this webinar is kind of predicated on the kind of impact we've been able to have, the kind of operations, the kind of feature and tooling that we've had to build to support 30 plus domains, let's say in a single organization, a team of 12,000 developers across domains trying to ship API iterations over the last couple of years, and allowing this team to go from an idea on paper to production in less than 100 days with new applications. And to kind of demonstrate about 75% reduction in the cost to develop new APIs in a repeatable fashion. That's where a lot of the learnings come from. And that is what you're going to see in action in the architecture and our implementation towards the end as well. So with that preamble, I will get started by talking about Act 1, which is the chaos. Over the last couple of decades, there have been several kind of movements, several kinds of several paradigms that have led to what we call microservices sprawl. I mean, not just we, there are other people who call it microservices sprawl too. There's a lot of chaos. There's tons of microservices, tons of databases. People are trying to kind of wrangle them together, trying to join them together, trying to make sense of it. And all of that has kind of happened as a result of the monolith to microservices movement. Now, in this webinar, I'm not going to get into the whole should you go with microservices or not. Facebook does monolith, so I will also do monolith. Not going to contribute to that debate at all. I think microservices are a pretty good operating model for several teams to kind of work together and have the independence to iterate on their kind of code and APIs and services in an independent way, and be able to contribute to an organization's API graph, so to say, right? If there's a better operating model out there, we're all ears. I'm sure the developer community would love that. But microservices or this style of operating in a domain based fashion or domain-based distribution of teams and engineers is the way of life now. And this life has some problems, and that is what we're trying to solve for. A couple of interesting anecdotes, something that some insights that I came upon personally recently. Um, a lot of what we are going to talk about, a lot of the chaos in the developer ecosystem is something that you can attribute to one phenomenon, which is there are now several databases and several types of databases, right? Um, and this has happened, of course, because of decomposition of a monolith into microservices. Earlier on, if you joined an organization, there would be a very top-down approach or a tribal approach to building on top of a single database or maybe one or two purpose-based databases. One language framework or a stack choice that has been made, and maybe one or two front-end application frameworks as well, right? The entire organization would kind of operate in this model. And the moment we decomposed a monolith into microservices, each team could now ask themselves the question of what database should we use? Is this the right database for us? Is this the right language and framework for us? So there's been a proliferation of new databases, primarily new database development and new database adoption, primarily because of this microservices movement. Because a lot of people were asking themselves the question of, is this the right database to use for this particular application or for this particular domain? The moment you have this, you have what you could call data sprawl. So each team could choose different databases. Each team could make that choice to begin with. And data itself is kind of sprawled in silos. There are disparate sources of data, not all of them connected together, because it's, of course, difficult for teams to talk to each other. So that's one moment. The other kind of insight that kind of blew my mind is, again, another movement that led to developers having to ask themselves the question, what database should I use? And this is the application modernization or the infrastructure modernization trends that, of course, we've all kind of seen, right? People invested a lot of money into on-prem infrastructure. Some of them have tried to move to public clouds. And as soon as you try to move out of your infrastructure from your own catalog of databases into a public cloud, you will have to answer the question of what database can I use? What database is offered here in this cloud? Can I run Oracle on this particular cloud or not is a question that a lot of developer teams have had to answer. And then they had to choose, okay, what other managed service can I use? What can I deploy easily on this particular cloud? What's possible to do on this cloud? And can I make a choice that works better for me than the incumbent database? So the movement from on-prem to public cloud infrastructure is another kind of trigger for folks to have asked themselves the question of what database can I use? What different kind of database can I use? And that is kind of what has led us to a very rich ecosystem of databases today. And there's, of course, adoption of that across different domain teams inside the same organization as well. And that makes this this chaos pretty intense in itself. So I thought that was a very interesting couple of insights on why we have the kind of the number of databases that we do and the option to choose, which has enabled developers to build APIs that work for their specific use case. So that's the context. We have lots of databases. We have lots of data sources. There is a sprawl of microservices. There's a sprawl of data itself in disparate or siloed data sources. And while all of this is happening, there's also proliferation of products, new products, mobile applications, web applications, integrated experiences. Your product teams are thinking about providing the best kind of experiences, the best kind of integrated experiences that takes all of the information about the user, is able to mirror that information in the form of meaningful experiences. And that unfortunately means having to talk to multiple domain teams. So if you have a set of products being built inside an organization, let's say the org's own web and mobile applications, you have stakeholders or partners who need to consume these APIs to build their own experiences. And let's say you have internal apps inside the organization for employees to make sense of what's going on. Each of these categories of products needs to work with all of the domains that you have in the system. Let me just turn on the pointer so I can do my hand waving more effectively. All right, so each of these classes of products, if you will, needs to interact with every domain that has meaningful information for them. And that is what I mean by integrated experiences. If you need to provide a good experience, you need to make sure that you're factoring in all the data that is relevant to providing that experience. We'll get into some examples in a few minutes, but it should be obvious that you cannot have a user interaction that does not take into account their footprint on, let's say, a team that is not the same as, let's say, the user management team or the billing team. Let's say there's another support team. You will need to bring in their experience with that support organization to be able to tell the user that, hey, this is your footprint on support. This is what you're doing with your authentication. These are the products that you've purchased and so on. You need to be able to build that 360-degree view. And for that to happen, you need to access data across multiple silos. And you need to be able to access this data in a way that is web scale. Of course, you want to benchmark for the traffic that you have and maybe 10x the traffic that you have. You need these APIs to scale, not just the APIs that you're building as a product team to consume these different domain APIs, but also the domain APIs themselves need to be web scale, because ultimately you're passing the traffic onto each of the domains. So the problem of accessing multiple domains, the problem of building APIs on top of domain APIs that need to be web scale, the problem of composition is a very tough problem to solve. And it's not very hard to imagine why, right? Because if you want if you want to build quickly, you will expect a consistent experience with each of the domain APIs. Now, domain one could have provided world-class semantics for filtering, pagination, and so on. And domain two has not thought about these things at all. And now, if you want to join data across these two domains, you're going to have a tough problem trying to understand which domain has what kind of capabilities. How can I join the data in a good way? Can I query the domain data in a way that I'm used to? Onboarding developers just with the right kind of information about what domain has what kind of APIs, what kind of capabilities, it's going to be a nightmare the moment you go beyond a couple of domains, right? So you need consistent experiences with the underlying domain APIs. You need to understand that the APIs that you build or the APIs that you consume as a product team are production grade indeed. What do we mean by that? They need to be performant. They need to have a certain latency threshold that they shouldn't cross. They need to have good observability so that you know exactly what is going on where. If there's something going wrong in the product, you should be able to pinpoint the domain where the failure happens and be able to fix that. You need consistent logging across each of these domains to be able to do that. And you also need things like perhaps caching or other features that make your API production grade. And all of this points to whether the domain APIs are quote unquote microservices ready. Do you have the kind of consistent quality across all of your domain APIs, and can you translate that consistent quality into good product APIs as well? So all in all, this problem of trying to make sense of data that is distributed across domains is a very hard problem to solve. And that right there is that snapshot of chaos, right? And you can kind of imagine, you can, it's easy to understand where the problems lie, right? Like if you kind of empathize with each of the different teams involved in this process. So let's just take two teams. One is this domain team and the other is the product team. So if you take a look at the challenges involved at each stage, both sets of developers is kind of struggling to make sense of this chaos. The domain team has to maintain APIs, maintain the schema, and figure out how to evolve this in a way that does not break things across the board. They need to have the right kind of guardrails to be able to operate in a world where they could be introducing a change that is only caught way down if you have good testing or in production, right? You need to, you've already kind of signed up to provide documentation and onboarding for the different stakeholders who are building on top of your APIs. So the responsibility of preventing drift lies with you. You need to make sure that there is consistency across the documentation, the API, the underlying, the domain databases schema or APIs. Ensuring there is consistency across each of these layers is something that you need to take care of while handling iterations. The same product team that will hold you accountable if there is drift is also the one that is demanding that you iterate on top of your domain API by adding access for new fields or new data and introducing new fields and so on. So being able to do this in a way that prevents integrity issues with the overall unified API is a challenge for domain engineering teams. And on the other side of this divide, the product teams, they need to work with too many APIs. They don't have a centralized registry to understand what data is available where, maybe not care about where this where a type or data is available. All you need to, in an ideal world, you should be able to look at a central list of data types, be able to consume them without bothering what lies underneath or what the implementation detail of that particular type is. And you need to be able to do this in a way that is clean so that you don't you don't duplicate your efforts in terms of data integration. And too often the same team. So you have this M cross N problem happening here. The product team needs to write glue code to join, let's say, domain one with domain two. The partner team also needs to perhaps do that. In some cases, if you have third-party APIs, multiple teams could be subscribing to that third-party API. First of all, you write the code. Second of all, you pay the subscription for this third-party API as well. And in fact, I do know of an anecdote where in APAC, a bank, a really large bank, they were subscribing to some regulatory API, a fairly expensive API, and several teams in their organizations had subscribed to that API. Not only were they paying, I think, 3x the subscription fees, three teams spent the time and effort to build an integration with that third-party API. And that's the duplicated data integration effort. Now, that's just with third-party APIs. Imagine having multiple domains internally. Imagine the time every team is spending on gluing these domains together, and the effort of kind of orchestrating things, which are very likely to be consistent. You're always almost going to want user information along with, let's say, their addresses, right? That's not going to change across your user-facing app products versus, let's say, your partner's product. These orchestration efforts are very likely to be consistent. The access patterns are very likely to be consistent. And regardless, the glue code is going to be fairly similar. And that's where you end up duplicating effort to integrate across these domains. And it's a hard problem. It's not an easy problem, especially when you run into all of the consistency issues that we spoke about previously. So providing access to multiple domains, or rather providing access to your own domain as a domain team, is a hard problem to solve. As a product team, consuming data from multiple domains is equally hard. So is there something that can kind of, I feel like there is this N cross M problem can be solved by maybe something in the middle, kind of brokering this exchange and making it easy for the different teams to be able to publish their data and to consume this aggregated data. And this is where a supergraph comes in. to solve this problem of publishing and accessing data across multiple domains. The idea of Supergraph is very simple. It builds on the same principles that we were talking about. The first core principle is that you need to think in graphs. Um, Now, this is not a Neo4j kind of database graph. We're not talking about graphs in the storage layer. We're talking about graphs in the domain modeling, the entity relationship diagram sort of way. We're talking about a semantic graph. So the first core principle of a supergraph is that every domain thinks of itself as a producer of a semantic graph. Now, once you do this, each domain is able to publish what you could call a notional subgraph. And each of these subgraphs, the moment it is semantic, can be aggregated into what you might call a supergraph. So if you build the subgraphs in the right way, with the right semantics, with the right type annotations, you automatically get composition on top of these subgraphs. And almost for free, you get a centralized registry. A product API builder, a product team should be able to look at what we are calling a supergraph, look at the types that are contributed by each of these subgraphs without having to worry about where these types are coming from, which subgraph does a type belong to. You should be able to look at a centralized registry and consume that type, know how this type interacts with other types in the registry, what are the kind of accessor methods that are available for me in this kind of data dictionary, and be able to access those methods. The problem of onboarding and documentation, all of these problems become super trivial the moment you build a semantic subgraph on top of your domains. If every domain does that, the glue code becomes I don't want to say trivial, but it does offer a lot of things for free for the consumers of the API, including a centralized registry, including a consistent data integration experience. In fact, it takes away the data integration problem because a supergraph can do that for you. The orchestration is something, those of you who've used API gateways before, you must have seen some of these orchestration capabilities. They tend to be relatively limited in the sense of the degree of composability you can have. I think that the kind of graph that you can build is relatively limited, but the principle is the same, that you have two independent domains and you're able to call APIs from these independent domains in a particular sequence or in a certain pattern. Introducing things that we're going to talk about in just a bit, things like GraphQL, introducing semantics or type semantics, or introducing a type system, you can elevate that experience to be very, very interesting for API consumers. And we'll talk about that in just a second. But the core principle is every domain exposes a semantic subgraph, exposes types which are consistently understood across all domains. You have a consistent way of publishing your data, and a supergraph layer which leverages this consistency to provide that orchestration or the composition layer, and all of the benefits that ensue from it. Fundamentally, you got to think in graphs though, right? Let's take an example to understand this, right? So a typical e-commerce example, these are the easy examples to go to. You have users as a domain, let's say. We have orders as another domain. And let's say you have catalog or products and brands as another domain. Typically, you need to access these domains independently or sometimes together. And as an engineering team, it's very likely that for each of these domains, I'm going to go back here. You may have a few REST endpoints to expose, let's say, users and addresses, maybe users and addresses. You have a list endpoint and an individual endpoint for orders, and the same for your catalog as well, right? Let's say that's the starting point of your journey. Every time there is a request for a new endpoint, you need to write up a new REST endpoint. If somebody comes and says, hey, I want orders, let's say the product team wants orders, the user who's associated with that order, and the address of that order. Of course, from a delivery perspective, that makes sense. You want to know what are the products involved, who are the users, and more importantly, what's the user's address, because I'll get a box, I need to deliver that. So you want orders.user.address. Now, if you had to do this independently, you would have had to build this third API by gluing together the data from each of these endpoints that the domain exposes. Now, what you can do is, instead of trying to make individual requests to independent domains, by getting a composed API, and we're going to use GraphQL, a lot of benefits to that. But it's an implementation detail. But if you hang on to the idea that GraphQL is a way to kind of introduce this composition, GraphQL is the way to get that type system in place, there are a lot of benefits. And the first pitch for you as somebody who might evaluate this is, if I get composition for free, then I don't need to write this third API. If I have a user endpoint, if I have an address endpoint, I have a user with address endpoint, and I know that order.user ID is the same as user.id. The glue code can take care, the supergraph can take care of the composition, and you as the consumer of this GraphQL endpoint or the unified supergraph endpoint, you only need to be able to say, I want users and their address. How you join these two, or eventually these two with an order, is completely taken care of by the supergraph layer itself. So you don't need to worry about the custom endpoints or the discrete endpoints that a domain exposes. You just need to look at what are the entities in my graph. What are the entities in my semantic graph? I have users have addresses, and orders have users. So can I stitch all of them together? Yes. The relationship is defined, the implementation of how this is glued together in a performant way, taking care of the usual distributed API orchestration problems like n+1 and so on. The supergraph takes care of that for you. As the consumer, all you care about is, where is the data? How can I stitch it together and get it to build a good experience for my users? So you just consume this data. You shouldn't, or rather, no one should have to duplicate the effort of doing this across the board. Product A, product B, everyone gets to access the same unified graph, and you write less code. You take less time to build, take this new feature, this new iteration to the market. And all of that, of course, will happen only if you need to write less code, and all of this is kind of taken care of for you. So that's the first pitch. If you allow composition via something like GraphQL that can just kind of going back to our example, allow you to annotate the types each of the domains exposes, leverage this information to kind of compose them together, and then provide a consistent API for the product team to be able to fetch that data however they want, without requiring the domain teams to duplicate or rather to expend more time and effort building out discrete endpoints, right? That's the first pitch. Composition allows you to write less code. Again, kind of elaborating that example, each on the left-hand side, you will see different permutations of a GraphQL request. And the pitch is that if you support the user entity and the address entity and maybe even the order entity once, all the permutations that you see on the left are taken care of by just one endpoint. You don't need to write new code to support these permutations. You will get a response based on the effort that you put in to kind of support these domains, the user and the orders domain. So you get more with the same code or config. I say config for a reason. I'll get to that in just a bit when we get to the implementation. So that's first pitch. Less code, write less code, do more with what you already have, make sense of the APIs that you have or the databases that you have, and be able to compose on top of them. Building on top of this composability, the fact that each domain exposes types, exposes information about how these types might be related to each other, allows us to kind of, again, doubling down on the point of composability, build a supergraph based on individual domains. So this is what you can do. You can seamlessly add orders or other request orders information because you know how orders are related to users. Users have multiple orders. Orders will have one user. Orders can have multiple products, right? So the notion of relationships between types from different domains is very easy to capture if you have the kind of subgraphs that we were talking about. So that's page number two, the composability. So in the previous example, we were taking a look at inside the same domain, how does composition work? The same team writes less code to be able to support various permutations of requests inside the same domain. And the same concept kind of is extended by composing subgraphs into a supergraph as well. All thanks to being able to describe the types and how these types are related to each other. All of it should be configuration. Nobody needs to write code to expose the semantics and then implement the semantics of these relationships. So that's pitch number two. Pitch number three, like I said, is once you have types, once you have information about these types, you can always introspect. You always have information about what the API supports, what to expect from it. You can always understand that ID is probably a UUID field, name is a varchar 50 characters, address, street, pin also has some semantics. You know exactly what to expect, and you can use this information to build API documentation at an org-wide level. Every subgraph, if we go back to our supergraph architecture, you know the types that are exposed here, you know the data that is available at each domain level, at each subgraph level, you know how they relate to each other. You, in theory and in practice, are now able to provide a very powerful centralized registry which has a self-documenting data dictionary, if you will. Right? You have a registry which is a unified list of all the types that are exposed in the system. You have a metadata about how these types relate to each other. And if you use GraphQL for kind of defining these types and the relationships between them, you also get the API documentation, the entity relationship graph, so to say, for free. Nobody needs to write this. Imagine the kind of unlock you achieve at the product team layer by knowing the full, complete universe of data that is available to you, the data and how individual pieces of data related to each other. In essence, it's a unified data graph, a super graph, and it is documented. And imagine the ease of onboarding new developers into this ecosystem of trying to consume from the supergraph for your team, for your partner teams. All the information necessary to consume the data is documented, and that kind of eases the kind of experience that you can build on top of this unified API. And just this semantic information makes life so much more easier. Instead of, let's say, looking at a list of discrete APIs, right? Very open API spec style, looking at 3 different endpoints independently is a significantly inferior experience to be able to see a visual representation of how the different types in your API are related. This is way more powerful. Anybody who's ever built or tried to consume a third-party API or an API that you haven't built yourself will attest to this fact. So that's pitch number 3. So less code, less documentation, faster iterations, faster time to market. That, in essence, is the pitch of a supergraph, right? And the last part of this webinar is a quick overview of how one can implement this supergraph. We call it Hasura DDN. It's our data delivery network. It's a combination of the supergraph architecture with some infrastructure components, which we'll get into. But what the idea behind Hasura DDN is, how can we provide a supergraph architecture in a way that requires the least amount of effort from all the different engineering teams inside an organization. How do we get to this architecture? How do we provide the building blocks of this kind of an architecture to any kind of engineering team inside an organization? That's the principle on which Hasura's DDN is built on. So it implements a supergraph architecture, and it also takes care of some operational aspects of deploying this supergraph as well. So think of it as a managed supergraph for yourself and your organization, where we can go from a domain data source, whether it's a set of APIs or your databases, and be able to provide them ready to be consumed by product API consumers or product users, no matter where they are in the world. So um, architecture, deployment, and guardrails to be able to operate a supergraph is what makes Hasura's DDN, data delivery network. The principle is to go from data to supergraph as quickly as possible with as much automation as possible. So we kind of extend the thinking in graphs to kind of switch the supergraph with a data delivery network. It's the same kind of box that kind of works with your domain subgraphs. What we've done is we've kind of decoupled the graph from the format in which the data can be consumed. So while we use GraphQL for implementing the supergraph, you can provide a self-serve GraphQL, REST, gRPC, or whatever network, or whatever format of API or interface that you are interested to your consumers as someone who's building the supergraph, or someone who wants such a supergraph. In a way that takes the subgraphs from domain teams, provides them the guardrails to be able to say, hey, I'm iterating on domain B, I'm making a change X. Can you quickly tell me if this breaks the semantics or the types or the integrity of the schema that was previously exposed by this supergraph? So Hasura's DDN provides the self-serve interface for consumers, and for the producers of domain APIs, it provides the guardrails to be able to iterate quickly by giving them very quick feedback on integration testing. In a nutshell, that's integration testing. To be able to get that test feedback early in the SDLC is what we call federated CI/CD, and being able to provide this kind of accelerated SDLC with the guardrails of not breaking your unified graph is what the promise of microservices was meant to be. And we're now kind of providing that while taking care of the composition problem. That is what Hasura's data delivery network does. And it extends that by taking this composed graph and kind of implementing it as stateless, serverless entities that can be distributed globally. And that's where the delivery network aspect of it comes. So it takes the data, it is able to make it available in the form of a stateless serverless API server. Serverless API server sounds very weird, but you get the picture. It's a function that is available, that is stateless, and it can be distributed globally. And the runtime is made available wherever your users are. And should you combine it with the magic of, let's say, distributed databases like Spanner or Yugabyte and so on, the experience of the user's request hitting the closest Hasura DDN node and the closest database node is extremely magical. And we have some demonstrations out there already, and we'll be doing more sessions on that. So please look out for that. But the key concept here is that the runtime is distributed, it is stateless, and it is serverless, making it very conducive to be an immutable version of your supergraph API itself. And that makes for very interesting operational implementations, right? I'm not going to get into a lot of that in today's webinar, but we'll deep dive into the CI/CD aspects of it, the benefits that you get in terms of being able to do HA, blue-green deployments, or whatever you want to do when you make this distributed runtime, stateless, and serverless. So we'll talk about that in a future webinar, but suffice it to say for now that you have the data access nodes ready for distribution across the globe, right? And how do we do that? By helping teams generate subgraphs on top of their microservices or data sources instantly. Has just come up with a data connector spec. We call it the native data connector spec. It's a specification. Remember, we spoke about how every domain needs to have a consistent semantics in terms of to access the underlying data. You need to expose pagination, filtering, logging in a certain way, and so on. So we came up with a spec that guides developers in being able to produce rich domain subgraphs. So that's the open spec. It's a spec that is kind of similar to your OData GraphQL-ish specs, but it goes straight from different kinds of data sources and talks about the types that are being exposed, how they're being exposed, what kind of filtering, pagination do you get, and how will logging work, what kind of capabilities are exposed by the domain, and so on. So that's an open spec. You can contribute to it. I will add the link in the resources. We also leverage this NDC spec to build what we call connectors, to allow users such as yourself to build connectors that can take an underlying source, whether that's a microservice, a DB, or your own SaaS system or a third-party SaaS system, as long as there is some sort of schema to infer in the underlying system, or even in cases where there isn't one, you can use this connector spec to build a connector that works for your organization for a given data source. For example, if everybody, all the different domain teams in your organization have Open API REST endpoints, Open API compliant REST endpoints already in place, it's very easy for you to kind of elevate those APIs into a subgraph by just building one connector for Open API specification. In all likelihood, you won't have to build one. Most popular ones will already be built by Hasura. But should you run into any kind of an edge case, the spec is available. There's a lot of tooling available for folks who want to build connectors on their own. I believe Tristan is on this call and he's churning out a connector every week. So it's very easy for you to take a domain, whether that's a database or a particular flavor of REST endpoints, or maybe even gRPC, and be able to expose that as a subgraph that can be composed over. So that's what Hasura's connector and the connector spec allow you to do. So that's the foundation on which Hasura's data delivery network has been built on connectors. And yeah, like Tristan says, it is very easy. Just follow his Twitter to know every week he's announcing one. And Hasura is also kind of in the business of building out connectors, so that if you're an organization that needs to work with, let's say, an Oracle database or a SQL Server database, you don't have to wait for a connector to be available. The connector will be ready in our connector hub for you to use. And you can deploy that connector consistently across your organization. You can tweak it and have a fork maintained for your organization if you're doing something that is very bespoke in your organization. So a connector is a way for you to impose that kind of consistency across different domains for any given underlying source. So that's delivery network on the composition side of things. And like we were just talking about, the connectors are what allow you to derive a subgraph from the underlying data source. The other interesting things that connectors do, or different kinds of connectors do, is they can also take your business logic code as input and provide a joinable command graph. What do we mean by command graph? So you have a read graph available from your source. Let's say, for example, you have a Postgres database, you have 5 tables, you have a Postgres connector. The connector will allow reads and writes and subscriptions and all of these kinds of good things to happen on top of the data that is in that underlying database. Now, let's say the CRUD aspect of the API is kind of handled, right? Because Hasura is able to infer the connector is able to infer the schema of the underlying database. It is able to allow you to choose what tables get exposed, and it has provided the read subgraph into the data delivery network. But you also want to have some kind of business logic. So let's say you are a TypeScript shop or a Node.js shop, and you want to write business logic that allows certain actions to happen on top of this data. What you can do is you can write your business logic in a language or framework that works for you, let's say TypeScript, and ask Hasura to take those discrete actions and add them as a command graph subset to this supergraph. If that makes sense. So you have in your supergraph, let's say articles, sorry, let's continue with that previous example, right? You have users, addresses, and orders. You also have, let's say, order delivery email, send order delivery email to user as a command available in your supergraph. So a front-end application, let's say there's a new uh, Apple Vision Pro kind of application that is being built by your organization where people somehow, for some reason, want to see their delivery notifications come through. So if you're building a new app, you can essentially use this command, this business logic, this send email business logic as a ready-to-use command in your supergraph. And you can implement that. You can extend this logic to other forms of business logic like validation and um, uh, uh, other examples of business logic, but a command graph is available for your developers to also leverage. And that's another piece of magic that the connector enables you to do. You can combine them. You can take a Postgres connector, expose the read graph. You can take a TypeScript connector, expose the commands, and kind of combine all of them into a super graph that knows that the command graph is acting on types from the read graph. And that is very powerful. Again, you know what is possible on top of the types that your supergraph is exposing, and you can enhance that with business logic, which nobody can generate for you. So, but you can write it in a way that is amenable to be incorporated into the supergraph thanks to the connector. The other good thing that a connector model allows you to do is in a federated model, your domains might want to have more control over the authorization of the models that are authorization on the data and the models that are exposed by the domain. So being able to expose predicates that allow you to filter on the underlying data and models makes it very easy for you to be able to compose a super graph that can do very interesting forms of fetching and filtering. We call it the composable read graph. To give you an example, if you had to do things like get me orders where the user's address is 50 kilometers or 50 miles from San Francisco. Now, that is a very hard problem to solve if you need to make two domains work together and neither of the domains has exposed the kind of predicates that you need to filter on top of each of them. And a connector model makes it easy for you to adhere to a set of predicates that can be exposed by each of the domains and then allow a composition on top of it. So connectors is our way of ensuring that the building blocks are amenable to composition, and that composability extends to predicates that allow for good authorization as well as good filtering. And that's what gives you a very powerful composable read graph. And that's the second aspect of the data delivery network. So a lot of good stuff on the super graph for the consumers of the API, and a lot of tools for the producers of the subgraph in a way that neither of the consumers or producers of this subgraph and supergraph have to, they don't need to put in the kind of effort that goes into writing up these subgraphs and supergraphs. So that's the principle. Those are the principles behind Hasura's DDN, implementing a supergraph in a way that minimizes the effort that is needed to build this unified semantic knowledge graph for your organization. And you can check it out at hasura.io. With that, we've come to the end of the webinar. I'm Sandeep. I'm available on Discord and on LinkedIn if you need to ask me any questions. A quick couple of reminders. We have weekly office hours in our Discord. Trishan leads those office hours. So these happen every Tuesday at 10 a.m. Pacific. So if you are interested in checking this out and in discussing this architecture model in more detail, please join us for our office hours. Thank you, Tristan. There's a link to our Discord. We'll add it to the webinar resources and we'll share it with you folks as well on email. And the other kind of reminder for our community is if you are a Hasura user, please do share your story at HasuraCon 2024. That is the Hasura User Conference. It's an annual conference where we get all of our users, indie developers, enterprises, all of them under the same quote-unquote roof to kind of exchange their stories, their learnings, and it's a really good event for folks to exchange their notes on best practices, problems that they're running into, to give the team the feedback, and to also just share the story. So if you're one of those users, please do check out the HasuraCon website. The doc is available there. You can sign up to speak at the conference and share your story. Don't worry about holding on to the resources. We'll send you an email with the links, but if you want to, you can also kind of just copy the link from the chat. All right. We have a few questions in terms of performance. Is using Hasura GraphQL suitable for real-time applications such as chatting? There is no reason it is not. Again, I'll kind of go back to the architecture diagram here, right? So give me a second. All right, let's take this question in the form of this product, right? So you have a front-end application, you need to enable chat. You have a domain which has, let's say, chat messages and in a table in a database, and you have a subgraph that exposes a subscriptions on top of these kind of models, right? We've implemented this in a form in Hasura's V2 in the current version, that is the long-term support version. We've enabled subscriptions on different kinds of databases, and we've implemented two kinds of subscriptions. One is a live query that implements more of a polling pattern. And you can decide how often Hasura polls the underlying database and whether you can batch the requests from multiple users. So in the case of a chatting application, it's very likely to be get all of the messages that Sandeep can see in this chat application. And let's say Tristan, who's another participant in the chat, is also trying to get their messages. So both of us are running the same WebSocket query, get my messages, for the lack of a better way to describe that request, where user ID equals, let's say, 1 for me, 5 for Tristan, right? So Hasura provides the semantics for you to define how to join, how much to join such similar requests. Maybe I want to cap it at 10 users. I don't want to batch requests from more than 10 users because the eventual query becomes very huge. So you can choose how much to batch and how often to query the underlying database. Again, this is for the live query model, which uses polling. You get a lot of controls on choosing how much load do you want to put on the underlying database. If you want to, you can hit it every few milliseconds and provide as near real-time an experience as you want to, and not batch at all. If you don't batch, the number of requests that go to the database go up. But let's say you have a super powerful database and not a lot of scale at this point. You can choose to keep the batching low, keep the polling interval as low as possible so that you can constantly bombard the database and get back the messages for the user. As your scale goes up, as you start hitting the limits of what you want to do at the database layer, you can increase the batching and reduce the polling interval depending on the kind of activity that is going on in the chat room or in your application itself. We also have like a change data capture equivalent implemented, the second kind of streaming subscription implementation as well. And both of these can help you implement a chat application. The performance is good. There's a lot of nuance involved. Like I said, if you kind of understood that entire journey of what goes into implementing different kinds of subscriptions on an underlying database, you have a lot of levers to both optimize the performance and to screw it up if you don't have them configured in the right way. So we have users who use Hasura Cloud, and they support about 10K concurrent requests, all of these resulting in multiple subscriptions. I think we've documented this somewhere or the other. There have been cases where we've had to intervene and help folks optimize the query, optimize these batching controls or the polling controls to get the right kind of performance. And in some cases, users have done it themselves. So we have users who've kind of built real-time chatting or concert applications where the scale goes from 0 to 10,000 concert participants in about half a minute. It's possible to provide performant real-time capabilities using Hasura. It just needs some careful consideration of how you want to do this and what are the trade-offs you want to make in terms of investment at the Hasura layer, at the database layer, and the latency that you are willing to provide. It's no different from a custom implementation, if you will. We've tried to optimize it as much as we can. So that's the long-winded answer to can you support? And Tristan shared a blog post. There's also some documentation on how you can optimize this. So we'll share this with you separately as well. I hope that answers your question. All right. Any other questions? We are a couple of minutes over time. I would love to thank you all for making it to the webinar. I'll quickly switch over to the reminder slides. Officers will help you with questions exactly like this. We can get into more details. You can share a screen and look at documentation and even your code and configuration. So please do join us there. And if you're a Hasura user, would love to see you at HasuraCon. With that, if there are no other questions, I will take your leave. Thank you again and see you at our next webinar. Have a nice day, folks.